maybe we should get started. People will continue to trickle in, but welcome everyone to this week's edition of the Physics Colloquium. We're lucky to have our speaker today, Cacey Bester. Um, Cacey did her undergraduate work at Southern University, did graduate school at University of Chicago, and then went on to do postdocs at Duke University and the University of Pennsylvania, and then is presently a faculty member at Swarthmore College. And so take it away, Cacey. Thank you for giving us this talk.
Yes, thank you so much for having me. It's a great pleasure to have this time to share a bit of the work that I'm doing with you all. During this talk, I'm going to share how we use the mechanical probing of impact as a way to learn more about granular systems. So the types of materials that I'm interested in are materials like sand. Sand may seem like a really simple material. So a pile of sand would just be thousands of tiny grains that are non-cohesive and have interactions just by contact forces. But sand actually is a really interesting material to study because it serves as a nice prototype for a far from equilibrium material. Something as simple as a pile of sand exhibits complex problems that come from studying materials that are characterized by disorder. Also, the sand grains interact with each other by nonlinear force propagations. So the force is not proportional in a way that is easily described, that can be easily described or understood. So understanding more about how to describe materials as simple as sand can have broad connections to other statistical and dynamical processes that we try to understand when describing far from equilibrium behavior that's exhibited by disordered systems. Sand is just one example of the types of materials that I'm interested in. More broadly, this area is referred to the physics of granular materials. Granular materials are large collections of macroscopic grains that have interesting collective behaviors. And the examples that I'm showing on the slide here are just a few examples of items that would classify as granular media. Things as small as grains of sand or kernels of corn to large items like boulders along a mountainside or logs, all examples of granular media. Hopefully these examples give you a sense of the enormous range of sizes, shapes, and purposes that granular media can exhibit. And this shows that understanding the physics of granular systems can have implications to many different areas, from industry to geological implications. So there's a lot of effort in trying to understand the physics of granular systems. What brings about the complexity of the effort to describe granular media are some of the unique collective properties that a granular system can exhibit. So for those of you who have taken statistical mechanics classes, you've probably learned that we can describe many particle systems and find the average properties of those systems using the toolkit that we learn in statistical mechanics. However, because of the properties of granular media, we can no longer make use of the classical framework of statistical mechanics to describe granular systems. For instance, individual grains of a granular media are very large, so their thermal energy is much greater, the thermal energy is much negligible compared to the gravitational potential energy. And we can't use temperature as a way to describe granular systems as we would make use of in statistical mechanics. Also, the grains are constantly colliding with each other, interacting by friction and collisions. So the granular systems dissipate energy as they interact, as grains make contact with one another. We'll constantly need to have energy input into a granular system in order to manipulate the behavior of our granular media. And that inhibits our ability to use our standard framework from which to describe granular systems. Because of this, the study of granular media makes for a really interesting study at the intersection of statistical mechanics and material sciences. And it's a really interesting place for a person like me to work. Experiments in granular media serve as a really important tool for providing insight into the behavior of granular systems. At the bottom of my slide here, I have an example of a simple granular experiment that nicely shows the unique behavior of granular media. In the series of images, there are grains that are of two different sizes, indicated by the two different colors. And all that is done is that the container of grains is vibrated up and down. Now, entropy would encourage the mixing of these grains, but instead what we see is dynamical effects are more important and the grains segregate so that the larger grains are at the top of the container and the smaller grains are at the bottom. This phenomena is known as the Brazil nut effect. So the next time you guys are enjoying a container of nuts, then maybe you'll take note of this interesting phenomena that can be exhibited by granular systems with even pretty simple experiments. Oh, I think I forgot to note at the start of the talk, but you all are welcome to.
Cacey, I just want to make a comment about this.
Yeah.
If this was an equilibrium system under gravity, you would also get a segregation, but it would be it wouldn't be this sharp, and it would also be in exactly the opposite direction, right? That big heavy particles would go to the bottom and the small lighter particles would go to the top. And it wouldn't be a perfect segregation, but they would each have their own sort of characteristic scale height, the characteristic exponential decay of density as you went up. And because that decay would be faster for the heavier particles, you'd have more heavier particles on the bottom and more lighter particles on the top, which is exactly the opposite of what you're seeing. Mm-hmm. And you also wouldn't see clean segregation between the two. There's just an observation. Yes. This is just different in many, many ways from what happens in equilibrium.
Yeah, thank you so much for sharing that.
Okay.
Oh, and I have a question on your point too. So how should I think about this losing energy? Is this friction that gets turned into heat, or what is it?
Yeah, so by that I mean the grains as they interact by friction. And so in experiments, we must manipulate the granular system in some way, such as the act of vibrating the system or some way to get a dynamic response from the granular media.
Okay, so there you're putting energy in then.
Right. Mm-hmm.
Okay, thanks.
Yes, thank you so much. You guys are doing exactly what I was about to encourage. So you can stop me at any time and ask questions. And I think Eric is keeping an eye on the chat window. So if you'd like to share a comment that way, you can as well. Especially the students, I'm prepared to talk with you in mind. So I'll definitely feel free to stop me at any point if you would like to add to the conversation. Yes. What's particularly interesting about the behavior of granular media is that it can exhibit characteristics that are like a solid, liquid, or a gas, depending on how it's perturbed. The picture that I'm showing here is a picture that I took during time in Southwest United States at sand dunes. So for someone who enjoys studying sand, this was certainly a heavenly place for me to be. And while I was there, I took this picture. It shows the static configuration of these of sand as it's packed into these dune shapes, and was able to support me as I walked across the sand dunes. But it's also interesting to note that as wind would blow, a gust of wind blew, then I would see grains move along the surface of these sand dunes, forming these evolving ripple-like shapes along the surface of the sand dunes, showing this really fluid-like motion. So it nicely showed how we could see these features of a solid and of a fluid in granular media, and see these really nice pattern formation that can be exhibited by granular systems. So to enjoy myself a bit further, I played around more with the sand. So I'm sharing a video that I took with my iPhone that is pointed towards the sand. And all I did here was kind of playing around. I digged into the sand with my hand and watched the disturbance that happened as a result. So I like to play the video for you all so you can observe this liquid-like behavior that I saw in the granular media. So I just kind of digged into the sand and observed the result. We saw this nice fluid-like motion. It looks like a viscous fluid that that is kind of just moving along the surface of the sand as the layer of the sand erodes. So I'll play the video again for you all.
I just want to point out that there are features on Mars that have been long known that look exactly like this, that there's some kind of large-scale movement of the Martian surface resulting in cliff-like features at the end.
Yeah, thank you. Thank you so much for sharing. Yeah, it's really interesting. So that video shows how simple kind of disturbances to the granular media can cause a transition from the granular system being in a rigid configuration to flowing and having a fluid-like behavior. This image here serves as another way in which we could perturb our system and cause this transition from solid-like to liquid-like behavior. Let's say that I take that sand pile that I showed you at the start of the presentation, and then I just tilt the surface a bit, and then tilt it above an angle called the angle of repose of the granular media. And the result is that the surface layer of the grains start to flow once the pile is tilted above a certain angle. Just that act can cause a transition. And we see how different flow regimes can coexist within granular media. We get our fluid-like flowing at the free surface of our pile of sand, as shown in this representative image, to a more creeping motion that is promoted below this flowing layer because of the interaction of the grains above, to the more rigid and solid-like behavior at the center of our pile. These types of behaviors and flow patterns that are observed in granular media are a significant problem in physics that we don't have a complete theory to describe. So experiments like this play a key role in our pursuit to better understand granular media. The particular experiment that I'll share with you all today is that of impact. I allow some object, a solid object, to fall and penetrate into our granular target. And it serves as a way of looking at this nature of granular media, how it can exhibit the solid-like properties and fluid-like properties. If I were to drop a solid object into a pool of liquid, like water, I would see a dramatic splash of the liquid, and then the object would sink to the bottom of our container. If I instead replace the liquid target with a granular target, like what I'm showing in the image here, there are some similarities and yet some differences. While we see the grain splash in a violent way, as we would with a liquid, the granular media also acts to make the projectile almost very rapidly come to rest, and in this solid-like nature, as it supports the weight of the solid. So the act of impact shows this rapid propagation from one type of behavior to another as the granular media dissipates the energy from the projectile that has been impacted on the surface. The types of experiments here are simple tabletop experiments, but they are a really nice way to show the nature of granular media, to probe this type of behavior, and to make connections to the role of impact into sandy granular surfaces that can be exhibited in other ways.
Casey?
Yes, sure.
So if I shot a bullet, shot something, at a really high velocity, or if I had a meteor hitting the surface of the moon, I might see something that would look quite a bit like that picture, because if the object's moving fast enough, even though I was hitting a solid surface, it could actually partially melt the surface, and then stuff would splash away. And then as it got deeper, it would lose enough energy that wouldn't be able to melt it anymore, or the stuff that melted would refreeze. And so you could imagine winding up, and I imagine this happens at impact craters, that if a big enough meteor hits, it makes a crater, it makes a big splash, material goes flying out, but the meteor ultimately doesn't sink to the center of the earth. It winds up sitting supported by the elastic medium around it.
Mhm.
And what I'm wondering is whether that's similar to what's happening in granular materials, or if there's some fundamental difference there. And if the answer to that question is the next half of your talk, just tell me that, and I'll let you go ahead and answer the next half of the talk. But I'm just wondering about the difference between, would it be fair to just think about this as a localized melting followed by a refreezing, or is it richer than that because of the properties of granular materials?
Yeah, I would say it's a bit richer than that. I wouldn't directly connect it to this type of melting. But I can say that while I will not talk specifically about impact craters, I really love that you pointed out that aspect of the similarities here of what's observed with our granular media, in that even in our granular systems, we can see that the media kind of maintains the molding that's applied, that's imparted to it due to the impact of a projectile. And there are efforts to connect those kind of small scale results in granular media to more planetary scale impact craters.
Oh,
Yeah, and trying to develop scaling relations based on the depth and diameter of craters to the impact energy that could have led to those particular shapes.
okay.
Yeah, so thank you for pointing that out. That's an area of great interest, and it shows how these types of experiments can have many connections depending on where your interests lie.
I just want to point out something quick about planetary craters, and you cannot do this in a tabletop experiment. Planetary craters are explosive. There's so much kinetic energy coming in that original meteorite is destroyed. It turns into granules that orbit the planet. The size of the crater's diameter is usually 10 to 1 in terms of ratio of 10 to 1, 10 times bigger than the impact event. And so much kinetic energy is released as explosive and heat energy. There's naturally lots and lots of melting going on. It's clearly happening in the case of Mars again. So I don't think you can, NASA's tried to reproduce these kinds of explosive events for a long time. They even have a physical experiment involving a cannon shooting a high velocity projectile into something that gets some qualitative similarities. But it's not the kind of explosive crater simulation. It's really not the kind of thing you can simulate very well at tabletop scale. So I don't think there's much real applicability to the real structure of impact craters.
Okay, thank you. Well, I like the discussion about the impact craters, because that really nicely ties in with what I want to point out about the interesting features that have been explored in connection to granular impact. So not only looking at the morphology of impact craters, but also the role of the packing density of your granular target. For loosely packed granular media, you can even see the formation of jets. So the series of images on the left side of my slide here show the impact of a steel ball into a loosely packed bed of granular media. And as the kind of cavity formed by the projectile collapses in, you see a nice granular jet that forms that kind of explodes from the surface, which is a really interesting phenomena that's very fluid-like. There are also numerical approaches that have been used to look at particle scale interactions during impact, such as a couple of the examples that I show here, to look at the velocity fields around an intruding projectile in the granular media, or seeing how granular flows around some obstacle. So those are just a few examples of the avenues that people have used to explore granular impact and further investigate the rheology of granular media. So I'd like to talk a bit more specifically about the granular impact experiment by focusing in on the question about the force laws that govern the penetration of a solid object into a granular bed. My goal in doing so is to learn more about how energy is dissipated at the grain scale. So I'm going to share the progress in our efforts to understand this problem with two parts. First, I'll talk a bit about just the motion of a projectile in a granular bed, and we'll use those experiments to find position measurements that we can then use to develop an empirical force law. And then to better understand the drag forces that act on an object as it penetrates the granular media, I'll show you all a few experiments in which we use photoelasticity to get a sense of the grain scale response to impact. Let's start with our first series of experiments. In this experiment, I'll have a solid object. In this case, it's an aluminum sphere that's released from some height above our granular target. In this case, the granular target is sand, a large container of sand, and our target can be released up to a couple of meters above our surface to increase the impact speed with which the object impacts our granular media. We then film the process using a high-speed camera that films at about 30,000 frames per second. And I observe the target using the images from our high-speed camera. A mirror is placed near the impact location at a 45-degree angle. And that allows us to track this thin rod that I have attached to the projectile. So I track the rod as a way of learning the projectile's position as a function of time as it penetrates through the granular bed, and look at any tilting that the object may have during its penetration. As my goal is to focus on its vertical motion as it penetrates in the granular bed. By finding these position measurements, we'll use the position measurements to determine the drag force that's acting on this object due to its interaction with the granular media. Our goal in doing these high resolution position measurements is to then develop an empirical force law that will give us some insight into the way that the granular media then dissipates energy in this system.
Is this experiment always done with the same size aluminum head, or do you vary that?
That's a great question. I vary that, and I'm going to show a bit of the aspects of that experiment as well. I'll use projectiles of different shapes, and so we'll talk about that a bit later.
How heavy is this projectile?
It's actually really pretty light. It's just a hollow aluminum sphere.
Okay, thank you.
So, yeah.
How do you ensure that, like, when you're dropping the projectile is completely perpendicular to the surface?
It is not always completely perpendicular to the surface. So what I would do is exclude data for which there is a more significant tilt. So I would have to repeat the measurements in that case and exclude data for which there's a significant horizontal motion.
Okay, thank you.
Yeah, sure, no problem. After recording such an impact measurement, we'll get position data that looks like what I'm showing here, where the y-axis is the position of the projectile, with 0 being the surface of the granular bit. And the x-axis is the time after impact. So 0 is the point where our object first makes contact with the surface. So we see that the object approaches the surface, and then once it impacts, it rapidly reaches to its maximum penetration depth of only about 5 centimeters in this case. And the entire process happens in only about 40 milliseconds. But we can track that motion in great detail because our data is provided by images from our high-speed videos. And then we can repeat this measurement at different impact speeds to achieve our position measurements for a range of impact energies. And
Sorry,
we'll then use.
Could I ask just a question about that, about the experiment? How do you define z equals 0? Is that the moment when the sphere touches the surface, or is that the moment when the center of the sphere is at the height of the surface, of the original unperturbed surface?
When the bottom of the sphere first touches the surface.
Okay. Great, thanks.
Yeah, thank you. So I repeat this measurement many times at different impact speeds. And here I'm showing the average of a few measurements for each curve. And the different curves correspond to different impact speeds, which are achieved by releasing the projectile from different heights above the surface. By doing repeated measurements, that allows us to then build up the data that can be used to develop our governing force law based on the position measurements. We see that as we increase the impact speed, our position as a function of time curves follow the same kind of trajectory, but the projectile penetrates deeper with increasing impact speeds. We'll then find the velocity and acceleration from the position measurements in order to determine the drag force that is acting on the projectile due to its interaction with the granular media. To find our velocity curves, as shown on the right here, we differentiate the position curves and then use a low-pass filter to minimize the noise in the data. So I'm showing here the smooth curves that result from an average of several of the impact runs. Before the object makes contact with the surface, the velocity is gradually increasing. And then at time t equals 0, the point of impact, we find that the velocity rapidly decreases, coming to 0 in about 40 milliseconds. And interestingly observe that even though the objects are impacting with different impact speeds, they seem to come to rest at about the same stopping time. I'll then differentiate again to achieve our acceleration curves, which we can use to gain insight about the drag forces responsible for this motion. The plots on the right show the acceleration as a function of time, and the 4 different curves correspond with 4 impact speeds, ranging from about 2 meters per second to 6 meters per second. So we see that when the object first makes contact with the surface, it experiences this large acceleration as the object is rapidly coming to rest, shown by the peaks at very low times after impact. The objects then gradually come to rest, as shown by our acceleration approaching 0. And we notice these fluctuations in our value of the acceleration that are resilient to our smoothing of the curves. That indicates to us that that's some physical fluctuation that's happening as our projectile is penetrating and coming to rest in the granular media. And I'm going to actually show you all a bit later in the talk a connection to those fluctuations in the acceleration. Was there a question?
Oh, yeah.
Yeah, go ahead, I'm sorry.
Go ahead, Greg.
Is buoyancy a consideration here at all? Because the low impact one, 1.9 meters per second,
Mhm.
that looks like kind of a buoyancy response to me rather than a penetrating response.
Yeah, for the lowest impact speed, that there may be more of a, I don't consider buoyancy, but you're right in that at the lower speeds, the projectile is barely really penetrating the target significantly.
Yeah,
penetrating
so
the
its
granular
ability
media
to sort of
significantly.
float on this new liquid surface is enhanced.
Yeah, that's a good point.
Could I
Was
ask
there
you-
another comment?
Yeah, well, just a question. How do these penetration distances compare to the size of the sphere?
Oh, yeah, so that's a good point. The sphere is about 3 centimeters in diameter. So the case of the higher impact speeds above, I guess about 3.5, above about 4 meters per second, are when the target is then deeply penetrating into the granular media and now is below the surface. The entirety of the sphere is below the surface of the granular media.
Okay. I mean, the reason I
Yeah.
ask is that you might think that in the initial response, you have just a little piece of the, sorry, I'm waving my hands and I don't have my video on. Initial response, you have just a small piece of the sphere in contact with a small area of the granular material. And then as you get deeper into the response, the sphere is in contact with more and more of the granular material. And it seems like if you wanted to make a model of that, that would be a factor you'd have to take into account. Whereas if you had
Yes.
deeply penetrating, you would just have a sphere
Yeah.
surrounded by a bulk granular material. So there's two sort of different limits. And I was wondering which one you're in. And it sounds like you're in the first one, where it's a small piece of the sphere contacting a small area of the granular material.
Yeah, I definitely, I love that point. I love that insight. And I definitely have had to consider that, particularly when, to get to another question earlier, when I use different types of projectiles, then I'll get a more significant penetration, and I'll need to adjust for as you point out, the surface area that's actually interacting with the granular media, depending on how much it penetrates into the target.
Can you get measurements off the high speed of mass displacement or total number of grains displaced? I imagine the data is there, but it's probably very hard to get.
Yeah, that would be pretty difficult to get. I'm not sure how I could do that reliably.
You can't do it reliably. You can just sort of estimate the number of individual grains through some image analysis.
Yeah, maybe I can do that, or
because I think this is a factor. How many physical grains are actually in contact with this body? I could be wrong, but I think this matters.
Yeah, I think so. And I'm excited to show you all the photoelastic images a bit later, because then you'll be able to kind of get a sense of how the impactor is interacting with the grains. So we'll get to talk about that too.
Hey, big move. Sorry, I'm curious. What feature of the slow one were you looking at and saying it looked like a buoyant force?
That's not sharp. It's not a sharp dip. It's a more gradual dip. And it sort of reaches, it doesn't have a critical point. It sort of flattens out for a small time scale. None of the other profiles really do that.
Okay, all right, fair enough.
Okay, so now that I've shown you all my approach to acquiring our position data, we repeat this with the goal of getting several measurements that will get us to a way of describing the granular media. So in essence, our goal is to search for something that will describe the fluid-like nature of the granular media as a result of our impact process. And there are two possible ways in which we could describe it based on how our drag force depends on the velocity. This is in connection with how we would describe a fluid-like drag. So if our drag force is proportional to velocity, then we would connect it with more of a viscous type drag. And if the drag is proportional to velocity squared, then that indicates a more inertial type drag and will give us insight as to how to try to describe this drag force for granular media. So the way that I went about doing that was to determine the acceleration or the resulting force as a function of velocity. The scatter plot shown here gives a scatter plot for many of the impact runs with varied initial speeds. And each point corresponds with a separate trajectory. I then determined the acceleration and velocity at a constant depth, in this case at 2 centimeters below the surface of the granular media, and look for a relationship between acceleration and velocity as a way of getting the form of our fluid-like drag of the granular media. We found that this acceleration is proportional to velocity squared, leading us to gain insight into the fluid-like drag exhibiting an inertial behavior and being able to describe the momentum transfer as being a more collisional process. So in essence, these experimental results led to us finding a form of our drag law that I show here at the top of the slide. The sum of our forces are, of course, gravity, and then two force terms, our fluid-like force term that is proportional to velocity squared, and a static force term that becomes important as the object comes to rest. And we find that if we look at the acceleration and velocity relationship at different depths, then there is some dependence of both our drag force terms on the depth of penetration of our projectile in the granular media. So the full form of our force law should include a static term, which we refer to as F here, and our fluid-like term, which we refer to as HV squared, where both F and H should depend on the depth in some way. So now that we've been able to use these simple experiments of a sphere dropped into sand as a way of learning more about the dissipation in granular media, we have this nice empirical force model. But that doesn't quite get at what our ultimate goal is in the experiments, which was to learn more about the grain scale origin of these force laws. So it would be really nice if we could do experiments that would actually give us a chance to see how the grains are responding to impact, and then allow us to connect this empirical law to a stronger description of the behavior of granular media. So the way that we go about doing that is by making use of photoelasticity. We have an experiment that is now a quasi two-dimensional experiment where our granular target of sand has been replaced by grains that are made from a photoelastic material. We've done experiments where the grains are cut from acrylic sheets, or where the grains are cast using a urethane castable liquid to have softer grains. The grains are photoelastic, meaning that they are birefringent when a stress is applied. In the corner, I'm showing a video of me just holding a single grain. It's just a few millimeters in diameter, and pressing it between my fingers. As I apply a stress to this photoelastic material, we then start to see bright and dark fringes that indicate the level of stress that the grain is experiencing. So we can use such grains as a way of being able to visualize the granular response in our impact experiments.
Are these grains compressible at all upon impact compared to incompressible sand?
They are compressible, and we make use of that to get a significant enough measurement for us to be able to observe. So in most cases, the grains are acrylic, and those are pretty tough. I mean,
They're
they're
close
pretty,
enough to sand?
yeah, yeah.
Okay.
But depending on the experiment, we may use something softer, depending on the goal of the experiment.
Right.
Yeah. So the grains are placed in a kind of quasi 2D chamber between two plexiglass sheets in a vertical arrangement as a single layer of grains. And then our projectile is a disc instead of a sphere. We place this arrangement between two polarizers so that what we see is our polarized light. And there's a rotation of the polarization of light depending on the level of birefringence that each individual grain experiences. This approach to using photoelasticity in granular media has its origins in engineering as a way of learning the response of ordinary materials. But in the last maybe 15 years or so, it's made its way into granular physics experiments and is now used a bit extensively now in the granular physics community. Because photoelasticity serves as a nice way of quantifying the stresses that are experienced by grains in our granular media. If we were to do this type of measurement, say for engineering purposes with regular materials, you'll see that that stress propagates smoothly and in a predictable way. But in granular media, as I pointed out, is one of the interesting features of granular systems. Force dissipation the force propagation is nonlinear. So in any granular system, when it's perturbed in some way, there are some grains that will take the bulk of the stress, while other grains take very little stress. And you'll see that in experiments in which we use photoelastic materials to make your grains. The images that I'm
Hey,
showing
Cacey,
here.
could I ask something about your two-dimensional geometry?
Yeah.
If all the disks were the same size, in 2 dimensions, it's very easy for the disk to settle into a perfectly regular hexagonal lattice.
Yeah.
And that doesn't sound like a granular material to me anymore because it lacks the
No.
disorder. Do you do something to keep it ordered? Do you make them polydispersed?
Yeah, I'm so glad that you said that. I forgot to mention, I should have mentioned that it's polydispersed.
Yeah.
Okay.
And I didn't need to really mention it with sand. Sand is naturally polydispersed, but
Right.
since we're manufacturing these grains, we purposefully make the grains of 2 different sizes. They are circular discs of two different sizes. And so we force that disorder in the granular media.
And in something that's roughly a 50-50 mixture. So
It's a 50-50 mixture. Yep. Yep,
okay.
Exactly.
Great. Thank you.
Yeah. And in the results that I'll show, we have grains that are discs, but I've also done experiments in which we've done grains that are different shapes, which brings about a whole new level of complexity. So we've tried polygonal shaped grains as well. Yeah. Thank you for the question. So the so the images here show us just a few examples of how photoelasticity has been used to gain insight about the behavior of granular media. So even for the simple case of the sand pile, there have been experiments of creating kind of a 2D sand pile using the photoelastic grains, and then being able to nicely see the force propagation in this static configuration. These kind of lightning-like patterns that you see in the systems are called force chains. And so they show how the force is distributed unevenly in any of these granular systems. And that's the same type of approach that we use for our impact experiments. Our media now, our target is now the photoelastic grains, and our impactor is a disc that's released from some height above our surface. And then we film the process using a high-speed camera. So I'll play the video for you all now so that you can see not only the trajectory of the object as it falls through the granular bed, but we can also see the grains, how the grains respond to this impact.
So Casey, you said that you described the disk as falling. Is this 2D experiment being done on a tilted surface, so you still have gravity acting as well as inertia?
Yeah, the grains are vertically arranged, and the disk is allowed to
Oh,
fall
it's
under
vertical.
gravity.
Right, gotcha. Okay. Great.
Yeah, sorry, I
think
should have
you
made
said
that clear.
I didn't register completely. Yep.
Yeah, so the disk is allowed to fall.
Okay.
Yeah, but if you were to do a horizontal arrangement, then I guess you could drag some type of obstacle through the granular media.
Mhm.
Can I ask a quick question?
Of course.
So you're doing this experiment where you're dropping it, it's of course accelerating and then impacts and has to very quickly dissipate all this kinetic energy it's built up into these force change and whatnot. So that's kind of like one ensemble of the experiment where you're, in a sense, you're not really holding anything constant there. But you could imagine a different version of the experiment where you pushed on this thing with, let's say, constant force or constant speed at variable force. How, if you did something like that, like change the ensemble of the experiment, how is that going to change, for instance, the structure and dynamics of these force chains and all these other heuristic laws that you've gleaned?
So you would still observe these force chains that we're seeing here in the impact experiment. And that's a feature that's robust to granular systems. So even if we perturbed it by, like, as you pointed out, dragging an object at a constant, so that it travels at a constant speed, for example, you could still observe this kind of propagation of the force in this way, as the impactor or the obstacle is constantly making contact with new grains and creating this new network that propagates through. But thank you, that's a great question and a great kind of idea too.
Sorry, Casey.
Yes.
Do you know of any rheology experiment that people have done by using these photoelastic grains to see how yielding happens?
I know that there have been some experiments recently, but I can't say that I'm as familiar with this, using this to do rheological experiments.
Okay.
So that would be something I'd have to look into more, because I'm not as familiar with that area of work.
Okay, thanks.
Yeah, thank you.
So in this video, can we think of the lighting up of the pixels, so to speak, as how a signal is being transmitted through the medium?
You know,
I mean,
yes.
are you reviewing a communication network in these grains? Is that what you're tracing by this experiment?
You know, I guess that you could think about it in that way. The images that I have here are nice for providing qualitative information and something semi-quantitative, but we would need better image quality to be able to get more at the actual kind of magnitude of contact forces that are being transmitted as one grain comes into contact with a neighboring grain. And
okay, so does that mean there's like a threshold effect that if the contact force is too weak on a grain, you don't generate light?
Yeah, that's exactly right. That's exactly the case for
Okay.
these experiments in particular, because this, in order to be able to observe this in detail, I use a high-speed camera. And to get the time resolution, I'm sacrificing the image quality necessary for these particular experiments.
I fully understand
But there are other granular media experiments that are more static experiments. So in which the grains are maybe compacted or sheared in some way, and then a single image is taken of a static resulting configuration, in which you can take a really nice high resolution image and be able to get more quantitative information.
Right, in a similar small aside, real short. So the Prince Rupert drops phenomena, when filmed at 30,000 frames a second, gives some information. There was one experiment where they had 120,000 frames per second, and that showed a much different phenomena, much different communication network, much more information.
Mhm.
So you may think about trying to use, I know they're expensive. You may try to get 100,000 frames per second and see if it's any different. You know, if it's not any different, then you don't need it, obviously. But I think it's something to consider for this kind of work.
Okay. Oh yeah, thank you for the suggestion. So I'm just looking at the time. Eric, at what time should I conclude?
We probably want to conclude around 5, maybe, a minute or two later.
Okay. I just want to keep an eye on things so I don't go over. Thank you.
You certainly had a lot of questions to slow you down, so we want to let you get through it.
No, but that's great. I can stop at different points, so that's not a problem. I just want to make sure that I don't keep this too long. Okay, so now the first question that we should address before trying to make a connection to our force law that we found by dropping spheres into sand is determining how well our photoelastic response matches from what we observe by tracking the intruder's trajectory itself. So I show that here in our plot of the acceleration as a function of time. So this brings me back to those fluctuations in the acceleration that we noticed earlier when looking at the projectiles, the result of the acceleration from our position measurements of the projectile. The red curve is the unfiltered data of the intensity in our images as a result of the photoelastic response. And the blue curve is the result after we've filtered the data. We find in doing so that our filtered photoelastic response matches up nicely with a curve of the acceleration as measured from tracking the projectile. So this gives us insight to show the connection between our force chain propagation as observed in the photoelastic measurements with the drag force fluctuations that we determine by measuring the projectile's trajectory, and shows that those fluctuations are intrinsic to granular impact. As you all pointed out, it connects nicely with the discrete nature of the forming and breaking of force chains that is exhibited in our system. So based on that connection, that led to us drawing the conclusion that we can describe this inertial drag that we found empirically in our system to a collisional-based model in which the momentum transfer is occurring because of these sporadic rapid collisions with chains of particles as shown by our force chains. And those force chains then propagate perpendicular to the surface of the impactor as it penetrates the surface. Based on the connection between our observation in the photoelastic experiments with our empirical force model that we gathered from our position measurements, we'll then propose our collisional model. Now we just need to figure out how we can translate what we're observing and what we expect to, how do we translate that to our 3D experiments of objects in sand? So that brings me to the change in the shape of the projectile that we use. That was brought up earlier during the talk. So that was really nice lead into this. Since our force dissipation is due to these normal collisions that capture the inertial drag, or we're proposing, then by changing the shape of our projectile, we then change the interaction that our object has with the granular media itself. And that should manifest itself in a change in our inertial drag measurements. So to test this, we tried these granular impact experiments with several different shaped projectiles. We used cones of different kind of slopes to the tips of the cone. And the schematic on the right side of the slide here shows a sketch of a cone as our projectile as it penetrates through a granular system. The orange circle is meant to represent a chain of grains that collide with the surface of our projectile and then propagate normal to that surface. The forces occur along the surface of our projectile so that we can write the force as a result of a collision as the rate and change of momentum with respect to time, and get an expression that scales with velocity squared as we expect from our empirical measurements. Then if the collisions are equally likely to happen across the surface, then we can find the expression for our inertial drag by integrating over the surface area.
So Cacey, what was DG in that expression?
Yes. So DG is the grain diameter. So we're showing here the mass and diameter of the grain, the velocity squared of the projectile, and this cosine theta term accounts for the shape of the projectile.
So correct me if I'm wrong, but this picture looks like it's a picture in which you aren't considering the interactions between different grains at all. It's like each grain is independently coming in, hitting the object and ricocheting off.
So I consider the possibility of grain and intruder interactions as the intruder penetrates deeper into the granular system, but I do not consider secondary collisions among the grains themselves.
Right. Okay.
Yeah. Okay, and then that leads to me getting this expression here. We can, since we're using our cone shapes, we can express our integral for the surface area of our cone in terms of a simple parameter, the slope of the cone S, and find that our inertial drag should scale with the grain density, the cone width, and the slope of the cone, as shown by our expression here for h of z, the coefficient of our inertial drag that we determine from the empirical force law. Okay. And then I'll kind of quickly jump to the next punchline, since I see it's almost 5 o'clock now. So in short, we repeated the series of experiments that track the position of our projectile as it penetrates into a granular media, similar to what I described initially for our sphere. Now we're doing it for different shapes and looking at the difference in the inertial drag as a result. Our goal is to show that the inertial drag scales in the way that we expect based on that collisional model. And maybe I should skip to the results. So I'll skip here to our final result because I see that I'm pressed that I don't want to extend past time too much. So in this final result, I show the inertial drag coefficient h of z as a function of depth in the granular bed. And the colors correspond with our different cone shapes. The dark blue is the cylindrical shaped cone, and our dark red corresponds with our sharper cone. As you observe here, as we go to different cone shapes, we see a decrease in the corresponding inertial drag as we expected from our collisional model. We also conclude from the curves, something that was pointed out in one of our questions, the influence of the change in surface area of the projectile that's interacting with the granular bed. So we see an increased curve shape in these curves that we think is an indication of that changing surface area that's involved in the collisions with the granular media. And then to further connect the collisional model with our measurements, we perform the collapse of our data. So we scaled the data all by the expected dependence on the shape of our cones, the shapes of our projectile, as expressed using the parameter S for the projectile shape. And we find that in scaling the data in this way, the data collapses to a master curve that follows the expectation from our collisional model. So I'll conclude by just stating that we use impact here as a way of probing the transitional nature of granular media. And in doing our measurements of impact, both by using position measurements and using photoelastic imaging techniques, we were able to learn more about the fluid-like drag that is responsible for the dissipation of energy in our granular system, and nicely connected to being the result of sporadic normal collisions with the granular media. So I'd like to thank you all for your time and for the wonderful questions. And I'm happy to stay and take more questions if you have them. Thank you.
Thank you, Cacey. And let's all unmute and we can do the awkward Zoom clapping. That was okay. It wasn't so awkward. So, yeah, if there are more questions, just shout them out, or if you can't shout, type them into the chat, and I'm happy to relay them.
Yeah.
I have a question about scales. So your initial examples, you had these impressive sand dunes, okay, and you had a talus field below a cliff. And so the sand grains are what, I mean, a fraction of a millimeter, and the talus blocks are what, I mean, feet. So if you look at things at the same scale, to what, how much does the size of the particles matter with respect to what they do?
Yeah, I think that there are some phenomena that I think can scale to that of larger granular systems, so larger grains. So I guess it depends. Like there are some instances in which we can make connections to maybe say avalanche behavior at different scales but I'm not sure how much all granular phenomena that we observe with say, grains the size of sand grains would connect to boulders or or something at the planetary scale.
It's specific to that material that you used in your impact experiment.
Okay. Yeah.
Yeah, and it seems especially when you're doing impact, where it's this sort of interplay between the kind of scale-free granular behavior, but then also the energy scale set by the impacting particle and the energy scale set by gravity, and then also the energy scale set by the material of the particle. So it's
also surface area related, I think. This is why rock slides are fundamentally different than snow avalanches in their behavior. A lot of surface area in rock slides, so a lot more complicated contact forces, and they're a lot more unpredictable than an avalanche.
Yeah, and this is what makes the stuff that Cacey does so hard, because it's this mixture of the universal and the non-universal.
Riffing on, I actually had a similar kind of flavor of question to what Dietrich had. I guess I would have anticipated in both either an empirical or, shall we say, like more, first principles type approach, that there'd be some non-dimensional parameters that should appear in any theory that tries to describe this. And two examples would be the relative density of the projectile to the relative density of the granular media that you're impacting. And then also, and this gets to the buoyant force question that Greg asked toward the beginning. And then on top of that, you'd also maybe have something like particle size relative to projectile size, another dimensionless parameter. So can you help me think about where these things that I'm pretty sure should matter, these dimensionless parameters should matter, somehow enter into our thinking here?
Yeah, those are great insights. And the results that I showed here apply to this particular type of granular experiment in which the projectile is far larger than the individual grain, and the density scales allow for such type of impact that we observed. But if we were to, for example, have an object that is closer to the size of our projectile, then we can see a different behavior altogether, and don't see this same type of scaling of penetration in our system, and may not see this same type of collisional model. Yeah, so that's a great point, and again gets to the complexity of this type of problem, because I've relied on work within a certain regime in which I could observe these type of impact, this type of response of the granular media from impact.
Thanks.
Yeah, but that's a great insight.
So there's a question from the chat from Francesco Cherry asking how the ramification of the impact on the granular media depends on the size of the grains. So this is sort of that cone that comes off of forces.
Yeah, so how the splash behavior kind of?
Yeah, what would happen if you used much bigger or much smaller grains? Would you get a different kind of sort of propagation front coming off of the impact?
Yeah, I think you would if you used different size grains, and in the reverse direction as well. If you had more of a powder than a granular, than something like sand, then I think there would be a different type of behavior that could be observed there.
I have a question.
Mhm.
So, like, how do these results depend on the surface texture of the projectiles? Because I would think that if the surface texture is textured with like dents and like regular dents and stuff, that would lead to a very different kind of like outcomes.
Yeah, at least for the types of experiments that we've done here, we do not see an influence on the granular response. So we still see the same type of force chain propagation that we observed before. Even if we had a projectile that had roughened edges or very smooth boundary to it. Now we do see a difference in the granular response if we for instance use softer grains, and the grains can compact and deform a bit as a result of the impact. Then we see more of a kind of a rigid cluster of the granular media that kind of travels with the impactor in a way, and it looks less collisional, as we showed for the particular case of these experiments.
Have you thought of doing your same experiments with mixed grain sizes?
I have, and it's one of the many things on the to-do list.
Okay.
Something that I can go back into a lab at some point.
Because I think that's a good way, because I think this is what a rock slide is.
Yeah.
Right? And why a rock slide is so complex is because if you have mixed grain size, you have different thresholds of forces that will contribute to signal propagation.
Yeah, definitely. There are so many things left to play around with, including that.
All right, well, if there aren't further questions, then maybe we can awkwardly clap for Cacey again and thank her for her time and for such a nice talk.
Thank you.
Thank you.
Thank you so much.
Thank you.
Hey, Dietrich.
Bye-bye. Thank you.
Sign off, and I think I'll end this meeting for everyone. So, bye. Thanks a lot, Cacey.
Thank you so much. I'll talk to you soon.
Got it.